Hello, and welcome to our first virtual lesson for AP Chemistry on atomic structure and the periodic table. So I'm going to take you through some super basics, okay? So this is you need to remember this from honors chemistry, but this is absolutely a tiny part of the whole thing, and we're going to go way more into depth later this year. But these are just those very basics that you need to know. Okay, so super brief overview of the history of the atom. Way back in 5th century, people are like, what is the world made up? And they're like, well, I think that everything is made up of tiny, tiny little particles. Like, in other words, every big thing we see could be taken down to something tiny. And they called that atomos because that meant indivisible. And so, of course, that's where we get our word atom. Aristotle believed that matter had our 4 elements of fire, wind, earth, water. So then jump way ahead, and we've got in 1807 Dalton's atomic theory. And Dalton's atomic theory holds pretty true, which to me is incredible that he came up with it in the 1800s. But all matter is made up of atoms, which are the smallest units of an element. That is kind of true. They are the smallest units of an element that still retain its properties. But we do now know that there are things smaller than an atom, and that, of course, would be our protons, neutrons, and electrons. So we do know that things are smaller, but they are made up of atoms. It's the smallest that retains its properties. All atoms of the same elements are identical, almost. We do now know that we have isotopes, which we'll talk about. But they are all the same in the proton number. Atoms of different elements are different. Absolutely true. Compounds consist of atoms of 2 or more elements combined in small whole number ratios. Absolutely. We're never going to have decimals or anything like that. And chemical reactions are rearrangements of atoms to form new products. Atoms are never created or destroyed. That is true, except in nuclear reactions, which of course Dalton didn't know about. So for the most part, this holds up pretty well. So after Dalton, we start having people discover the individual parts of atoms. So Dalton knew of atoms. Now we're getting to people learning, okay, well, there's stuff inside those atoms. So first we have J.J. Thomson. He used a cathode ray tube where he found that something in the ray, when he put a positive charge, forced it to come towards it. So what that means is whatever that thing is coming towards the positive charge was negatively charged. And so that means he found the electron. He, though, however, thought that the electrons were just randomly dispersed throughout the positively charged atom. So he didn't know about protons, didn't know about the nucleus, but he did find the electron. So then we move to Rutherford, who did a gold foil experiment. So where he took a piece of gold foil and he shot alpha particles at it. Now, alpha particles are positively charged. He expected them to all mostly go through the atom at an even rate. But what he saw is that a lot of the alpha particles were shot back, and only a few of them. And so what that showed him is that there was something in there that was positive, that was deflecting the positive back, because opposites repel. And then all of that positiveness was very tinily in the center, densely packed. That showed us the nucleus and the proton. So, in other words, an atom is mostly empty space. Most of his alpha particles went straight through the gold foil. But there's a small, heavy, dense, positively charged mass in the center, and that's the nucleus. And then in that nucleus has to be something positive, because it was when the alpha particles hit that they bounced backward. And so that is our proton. Next, someone whose last name was Soddy identified isotopes. So we'll talk about those in a second, but that showed that not every single atom of an element is identical. And then someone named James Chadwick was the one who finally found that particle that was about the same. mass, size of the proton, but no charge, and that's our neutron. And if you ever wondered, James, the nickname for James is Jimmy, and so that's where we get the name Jimmy Neutron. Okay, so we've discovered all these particles. What are they? So our subatomic particles, meaning smaller than an atom, they're inside, are our proton, neutron, and electron. We know that our protons and our neutrons are inside of our nucleus. Those are the two particles that make up the nucleus of an atom. The electrons move around outside in the electron clouds. Now, later in this year, we're going to talk so much more specifically what these electron clouds are, where these electrons are, orbitals, shapes, all that good stuff. But right now, we're not going to get into that. You just need to know that protons are positive, neutrons are neutral, they're in the nucleus, and then the electrons are outside the nucleus, and the rest of it's empty space. There's nothing else. So when we're looking at, say, the periodic table, and we're looking at an element, we can tell from the numbers the information about its subatomic particles. So the atomic number of an element is its number of protons. That's that main number you see on the periodic table. That's the way the periodic table is arranged. Okay, so the number of protons is unique. Sorry, I'm trying to write on the screen. Unique to each element. So you can think of it like a fingerprint. So if I say 47 protons, it has to be silver. Because if I say 48 protons, then I'm talking about cadmium, and if I say 46, I'm talking about palladium. So if we say proton number, it's only one atom we could possibly be talking about. All right? The other number that's on the periodic table is the mass number, and that's protons and neutrons. And there's a reason why it's a decimal point on the periodic table. We're going to talk about that in a minute. But if we're given the mass number and we are given the atomic number, we can subtract the two in order to get the number of neutrons. And then if an atom is neutral, the only way for it to be neutral is that the positive has to equal the negative. So that means that the protons equal the number of electrons when neutral. So the way it's written on the periodic table, it's neutral. So again, if we look at this silver, then we have to have 47 protons and 47 electrons because it's a neutral atom. All right? So let's just do a few examples. All right? So we have copper. It is going to have 29 protons, and then it has 63 minus 29, which is, mental math, 34 neutrons. All right. Magnesium has 12 protons, and then it has 22 minus 12, so it has 10 neutrons. Copper, 6 protons, 12 minus 6 is 6 neutrons. So that is absolutely something that you need to be able to do, is you need to be able to be given a symbol like this, and you need to be able to identify what element it is, how many protons it has, how many neutrons it has. I'm not given a charge for any of these, so I have to assume they're neutral. So that means that we also have 29 electrons for copper, we have 12 electrons for magnesium, and we have 12 electrons for carbon. So we're not given any sort of charge. Ions are another way that atoms can be different for the same element. So an ion is an atom with a charge. So we don't call an atom an ion unless it's charged. All right? The only way to become charged is protons and electrons are not equal. All right? But remember, protons are the identifying factor. Never change protons. So if something becomes positive, it didn't add protons. If it did, it wouldn't be the same element. It lost electrons. Okay? So we have anions, which are negative because they gained electrons. And then we have cations, which are positive because they lost electrons. The electrons change, not the protons. All right? One way I always remember this is cats have pause, so they're positive. So cations are positive. All right? So magnesium was on the previous slide, but it didn't have this +2. So for magnesium, we already identified that it had 12 protons, 22 minus 12, 10 neutrons, and before we said it had 12 electrons because it was neutral. Now it has a +2 charge. So the only way to have +2 is to lose 2 electrons. And so this thing must have 10 electrons, which is where we get that +2 charge. Okay? So I like to think of it like if I hang out with more negative people, I become more negative. So if an atom gains more electrons, which are negatively charged, it gets negative. But if I get rid of those negative people in my life, I become a more positive person. So that means if an atom gets rid of electrons, the other way that atoms can be different of the same element is isotopes. So isotopes have the same number of protons. Remember, we can't change that, or we change the actual element's identity. But the neutrons change. We have a different number of neutrons, which means the mass number changes. Okay? So I like to think of isotopes like the same shirt in a small, medium. You go to the store, you're trying to buy a shirt, and you're looking through the rack. It's the same shirt, the same color, it's the same material, all of it. Same design, everything. It's just different sizes. There's a small, medium, large, extra large, whatever. All right? Atoms are the same way. It's the same atom. So for the example right here, they're all carbon. They all have 6 protons, or they wouldn't be carbon. But carbon 12, which isn't written here, has 6 protons and 6 neutrons. 12 is the mass number, which remember is protons plus neutrons. Okay. Carbon 13 is also carbon. It has 6 protons, but now it has 7 neutrons. Carbon 14, still carbon, still has 6 protons. Now it has 8 neutrons, which gives it that mass number of 14. So how do we know about these different isotopes or differentiate between them? We use something called a mass spectrometer. And later in the year, we're going to talk way more about how a mass spectrometer works. But right now, you just need to know that we can enter or put in a sample of an element. So in this case, we're doing zirconium. And it's going to go through the mass spectrometer, and it's going to exit it at different rates based on the mass. So we learned that isotopes have different masses because they have different numbers of neutrons. And so this detector is going to create a graph like this that's going to show the different masses for each isotope that's detected. So in this case, we got a zirconium 90, 91, 92, 94, and a tiny bit of 96. So that means that zirconium has 5 isotopes. The other thing it's going to show you is how often the detector detected those specific masses, and that's going to be our relative abundance. So for example, just over 50% of the whole sample were isotopes that weighed or had a mass of 90. All right? So over 50% of the sample is 90. So if we look at the periodic table and we look at zirconium, we see that it has a mass of 91.2. All right? That makes sense because 50 plus, let's say, 11, like 51 plus 11, so like 62% of all zirconium has a mass of 90 and 91. So it makes sense that this average mass is skewed towards 91.2. All right, so we call that the average atomic mass. So atoms are so small that it's very difficult to talk about their mass in grams. So instead, they created the atomic mass unit, and it's based on carbon. You don't need to understand that. But you just need to know that the AMU, atomic mass unit, is technically what the numbers on the periodic table are. So if you look at this example, it shows us carbon 12 and carbon 13. And it shows us that 99% of all carbon is carbon 12, and only 1% is carbon 13. So if we take into consideration the 12 and the 13, if we just found the average of 12 and 13, it'd be 12.5. But if we look at the mass of carbon on the periodic table, it's 12.01. That's because of average atomic mass, right? We take into consideration the relative abundance, the percent, all right? So for example, your categories for your grades, all right? If tests are 50% and homework is only 10%, if your test grades are all 30s, your homework might all be 100s, but your grade is going to be way closer to a 30 than a 100 because the category of tests has a higher weighted or higher weight. That's how average atomic mass works. So let's do an example of calculating the average atomic mass. So the formula for average atomic mass is that you're going to take the sum of the isotope's mass times the percent in decimal form. And you're going to add all of those together, okay? So percent in decimal form just means divide the percent by 100. Now, this is very easy if, like, let's say it was 85% becomes 0.85. When this gets a little confusing for students is when the percent itself is already a decimal, and especially even really small decimals like this example that we're about to do. Okay, so don't get tripped up by that. Just because the percentage is a decimal doesn't mean it's in decimal form. You still got to divide by 100. You still got to go to the left too. Okay, so we're going to do this example. We have an isotope that has a mass of 234.04, and we're going to multiply that. We're going to go over 2 by 0.00005 plus the next isotope, 235.04 times 0.0072 plus 238.05 times 0.99275. All right, we're going to multiply those and add them together, and we get a total of 238.05 AMU. If we look at the periodic table right behind us, actually, then we can identify that this is actually uranium based on its average atomic mass. Now, it makes sense that the average atomic mass is extremely close to this isotope's mass because over 99% of all uranium has that mass. Okay? All right. So last thing for this lesson, just a brief overview of the periodic table and how it's arranged. So we know that the periodic table is arranged by increasing atomic numbers. So we start with 1, we go to 2, 3, 4, 5, 6, 7, so on and so forth. And when Mendeleev created the periodic table and he arranged things by increasing atomic number, he saw a pattern, a periodicity. All right, so it put them into groupings that showed similarities. And he was able to predict even where missing elements were. So if we look at the periodic table and we have a column, we call those groups. Sometimes they're called families. Groups are going to be the most similar. So in groups, the elements are more similar to one another. So that's why sometimes they're called families. They have similar characteristics to one another. If we go across a row, we call that a period. All right, so in most periodic tables, we label these, so we've got like row 1 through 7. All right. So on the left-hand side of our periodic table, So to the left of what we usually call that stair step are metals. So our metals are on the left-hand side. Metals are great conductors. They lose electrons, so they're always going to be cations. They're going to be positive. They're very malleable and they're ductile. On the right-hand side of our periodic table are our nonmetals to the right of that stair step. So they're going to be very brittle. They're going to gain electrons, so they're anions, so they form negative charges, and they do our covalent bonding. Right along that stair step are our semi-metals or metalloids. They display properties of both metals and nonmetals. So some of them will be extremely brittle, but then they'll also have lower melting points. So they'll kind of have characteristics of both metals and nonmetals. Some of our groups have particular names. So the first group of metals is the alkali metals. Our second group are the alkaline earth metals. In the middle, we have our transition metals. On the right-hand side, in our nonmetals, we have our halogens, and then we have our noble gases. Down here at the bottom, and where they actually belong would be right here, but it's very difficult to show a periodic table on one page that would be that long. But those are our inner transition metals. They have a lot of our radioactive atoms. So the last thing we need to remember is that in our groups, some groups have elements that have the same charge no matter what. They're always going to form the same ion. They don't all, let me make this so clear. They do not always have that charge. So like if I have a solid block of sodium, those are neutral sodium atoms. They do not have a +1 charge, all right? That's like a common misconception. It's that when sodium forms an ion, it's going to lose 1 electron and become +1, okay? So our alkali metals are all going to have a +1 charge when they form ions. Our alkaline earth are all going to have +2 charges, always, when they form an ion. Now, you'll notice there's nothing here that has charges that stay the same, except for a few exceptions that we'll talk about when we're doing naming. Their charges vary. They have different ones, all right? Now we hop over to our nonmetals. These two are always going to be a -3 when they form ions. These are always going to be -2 when they form ions, and these will always be -1 when they form ions. So that's something to remember and keep in mind. We can remember that just based on their location on the periodic table. It's going to be important as we get into naming.